Okay, so I'm going to do two beam examples, and I'm going to actually just take them from the exercises from 3.8. So these are coming directly from 3.8.1. The first one I'm going to do is number 2, so I'm going to leave you guys to do number 1. Number 2 says a uniform beam of length 10 meters is simply supported at both ends. So I'm going to go ahead and just draw this. We have it. So 10 meters simply supported at both ends. So we've got at x equals 0 meters, at x equals 10 meters. If it's simply supported at both ends, that means we have 0 deflection at both ends. So at y equals 0, we have no deflection. And at y equals 10, we have no deflection. And then we will have slope if we are allowed to deflect between 0 and 10, but we won't have any bending moment at these endpoints of 0 and 10. And don't forget, we will not expect you to memorize what these boundary conditions are. These will be given to you on the last page of the exam. So we'll tell you simply supported y of 0, we'll tell you simply supported y equals 0, y double prime equals 0. You just have to figure out, how to apply that to which end you apply it to. Okay. So because it's simply supported at 0, this is what we have. And because it's simply supported at 10, we have these two conditions here. Okay. Let's see. It has a constant load distribution of omega of x equals 60 times Young's modulus times inertia, newtons. So the units are newtons. That n is not a variable, it's not a constant, that's your unit of newtons. Okay, so we're going to go ahead and put all this together in our differential equation. So this is just sort of our given information here. So the differential equation is EI fourth derivative of y is equal to our load per unit length. So putting in our load, we have EI fourth derivative of y equals 60 times EI. Again, your load is typically not written in terms of Young's modulus and inertia, but we're doing that so that the differential equation solution process is nice and clean, because now we can divide both sides by Young's modulus and inertia and cancel them out. And the differential equation that we are going to solve is a nice clean fourth derivative of y equals 60. Now, I know that there are other ways that we can solve this with integration, but this unit is specifically the unit in which we are solving differential equations using both a complementary part of a solution and a particular part of a solution. And we are having to assess you on the method of undetermined coefficients. So you need to solve the problem using those methods. All right, so it's really important that you do exactly that. I'll come back to these later when we need them. So let's come on over to the complementary part of the solution. So if you remember from class, Professor Bateman and I would have told you that it doesn't matter which situation you have for a beam, your complementary solution will always be the same. I will work through it again, but if you go ahead and just tell us what YC is without doing the work behind it, we're okay with that as long as it's correct. If you don't state it correctly and you show us no work, we can't give you any partial credit. So keep that in mind. All right, so the complementary solution comes from the homogeneous equation, fourth derivative of y equals 0. The characteristic equation is r to the fourth equals 0, which means r1 equals r2 equals r3 equals r4, and they are all 0. So that means y1 is e to the 0x. y2 would also be e to the 0x, but it can't be, so linear independence tells us we need to multiply by x. y3 should also be e to the 0x, but it can't be, so we would multiply by x, but that doesn't work either, because now this is linearly dependent, so we multiply by x again, giving us x squared. y4 would also be e to the 0x. Again, that can't be, so we multiply by x. That doesn't work. Multiplying by x again gives us x squared, which doesn't work. So we multiply by x again, giving us x cubed. And we know that e to the 0th is 1, so y1 is 1, y2 is x, y3 is x squared, and y4 is x cubed. And so our complementary solution is C1 y1 plus C2 y2, which is x, plus C3 y3, which is x squared, and then C4 y4, which is x cubed. And so this is our complementary part of our solution. I'm just going to do that little dotted box around it because I know I got to come back and grab him later. Okay, so I'm going to hold off, come back to this complementary solution in a little bit. Now I turn to my particular part of the solution. Now here, I notice that my right-hand side is just a constant. So I think for a moment that my particular design should just be a constant because the derivative of a constant is 0 and everything after that would just be 0. The problem is I already have a constant in C1. So if I multiply by x, that would give me linear independence, except I already have an x term. Multiplying by x again gives me x squared, which I already have. Multiplying by x again gives me x cubed, which I already have. Multiplying by x again gives me x to the 4th, which I don't have, so that's what I need. So you have to, again, check your particular against your complementary to make sure that everything that you're looking at is linearly independent of every other term you've already generated in your other solution pieces. Okay, so we need to take 4 derivatives of yp to plug it back into here. So I have 4ax cubed, and then second derivative will be 12ax squared. Third derivative will be 24ax. And then the fourth derivative will be 24a. So then what I need to do is put that into my differential equation. So the fourth derivative of yp needs to be 60. So 24a equals 60. So a should be 60 divided by 24. Both of these are divisible by 6, which I'm going to start with that because I know some of us are really working on our reduction. So that's going to be 10 over 4. Both of these are divisible by 2, so that means a is going to be 5 halves. And so my yp is going to be 5 halves x to the 4th. Excuse the background noise. I am doing this with the kids in the house and the dogs in the house, so apologies. Okay, let's just go ahead and check our numbers really quick. So we have 60 EI, so we had our 60 here. AX to the 4th, because we had to go up to the 4th power to get out of any of these powers here. 4x cubed, 12x squared, 24ax. Okay, perfect. So 24a, 24, 60 over 24. Reduce this by dividing by 6, 10 fourths. Dividing by 2, 5 halves. Perfect. So now we have both YC and YP. So just like before, all we're going to do is go ahead and add these two together to get our general solution. Y equals C1 plus C2x plus C3x squared plus C4x cubed plus 5 halves x to the 4th. So that's our general solution. And now our job is to find C1, C2, C3, C4. So that's 4 unknowns, which means we need 4 equations. That's where our 4 boundary conditions come in. Because I have y, I can use the first two conditions, y of 0 equals 0 and y of 10 equals 0. So I can use those right off the bat. Let's go ahead and plug those guys in. So y of 0 equals 0. So that means 0 equals C1 plus. Now every other term is going to be 0 because that's where x is 0. Which that's really nice because that means that C1 is 0. So I'm just going to go ahead and cross that off and call it 0. Now I can also do y of 10 equals 0. Keep in mind C1 is 0, so I don't even need to really plug that in. So 0 equals C2 times 10 plus C3 times 10 squared plus C4 times 10 cubed plus 5 halves times 10 to the fourth. And again, notice I didn't write C1 because I already know that that is 0. Now this is a part that I would hope everybody is a little bit more comfortable with. I would divide both sides by 10 because each of these terms is divisible by 10. So if I say divide both sides by 10, that also means divide every term by 10. So that's actually going to knock this down a little bit. So that gives me 0 equals C2 plus 10C3, right? Plus, this will be 10 squared, which is 100, C4, plus, this will be 10 cubed, which is 1,000 times 5 is 5,000 over 2. And 5,000 over 2, I can simplify to 2,500. So I'm trying to clean up my equations as I start plugging stuff in. So I still have I still have 3 unknowns, okay? But that's okay, because I still have 2 other conditions that I need to use. But in order to use these 2 conditions, I need to take the second derivative. So I'm actually going to grab another piece of paper because I need to take a second derivative here. I want to make sure I have enough space to work here as well, okay? All right, so the next derivative of y, so y prime would be derivative of C1 is 0. Derivative of C2x will be C2 plus derivative of C3x squared will be 2C3x plus derivative of C4x cubed, 3C4x squared. Now, bringing down 4, I'll have 5 times 4, which is 20 over 2, so 10 x cubed. Now I don't want y prime because my conditions are for y double prime. So I need to take another derivative before I can apply those conditions. The derivative of a constant is 0. The derivative of 2c3x is 2c3 plus 6c4x plus 30x squared. All right, I'm going to go ahead and remind you, we have y double prime of 0 is 0. Y double prime of 10 is 0. So we're going to see what that gives us. Okay. So y double prime of 0 equals 0. Let's see what that does. 0 equals 2c3 plus, now these 2 terms will both be 0, which then gives us that c3 is 0. So that's nice. Let's come on back up here. And everywhere we see C3, we're going to call it 0. Okay, so everywhere we see C3, we're going to call it 0. Okay, so now I'm going to go ahead and use another condition, the y double prime of 10 equals 0. Again, let's go ahead and call that 0. Let's call that 0. So y double prime of 10 equals 0. So 0 equals, that's gone, 6c4 times 10 plus 30 times 10 squared. All right, same thing. Let's go ahead and divide both sides by 10 because then I can divide every term by 10, and that's going to help me clean things up a little bit here, right? That's my goal, is to try to clean things up. 0 equals 6c4 plus 30 times 10, so 300. And you know what? I can clean up even more. 6c4 equals negative 300. I can solve for c4. C4 is going to be negative 50. So now that I know what C4 is, I can plug that in up here and solve for my remaining constant, C2. So I have 0 equals C2 minus 5,000 plus 2,500. Negative 5,000 plus 2,500 is negative 2,500. So if I add that to the other side, C2 is 2,500. So C1 and C3 zeroed out. C2 is 2,500 and C4 was negative 50. So my final solution is y equals C2, which was 2,500, x minus 50, x cubed, plus 5 halves, x to the fourth. Because the other terms, C1 and C3, were 0. And that's the general, or that's the particular solution, excuse me, for the deflection of this beam. So the simply supported beams, those ones tend to be a little bit more work when it comes to the algebra at the end, because yeah, you do have a little bit more work when it comes to solving the system of equations. You do have to take the second derivative before you can actually start solving for another constant. You get C1 right off the bat, but then there's a little bit more work to be done right away to get you have to take the second derivative before you can do anything. You get kind of stuck on your second condition here. Okay, but that would be your equation of deflection for this beam. Okay, now we're going to go ahead and do number 3 from that same set. Let me just get logged back in. Again, apologies for the background noise. Both 2 children and 2 dogs are in the house. So, okay, so again, we're looking at 3.8.1, number 3. All right, so this one says a uniform beam of length 10 meters. So same thing. But now it's fixed at x equals 0 and free at the other end. So now this one is going to be in cantilever state. All right, so we have something like this. So it's fixed at 0 and free at the other end, and it's 10 meters long. Okay, so if it's fixed, there is no deflection, and there is 0 slope at this side. And where it's free, we have no bending moment, and we have no shear force. Okay. It has a load distribution of omega of x equals 20 EIX, and that's in newtons. So that would be something that looks kind of like this, right? It's a linearly distributed load with a positive slope, right? Something like that. I went off the paper, but you get the idea. Whereas on the previous example, it was a constant uniformly distributed load. So it would be distributed horizontally across the beam. Okay. All right. So we're going to go ahead and set up our differential equation to solve this one. And no, you do not have to draw this. I'm just trying to get you all to see the picture. Okay. This is not necessary to draw for credit by any means. All right. So we have EI fourth derivative of Y equals load per unit length. So we're going to go ahead and put in our 20 EIX. Again, you don't have to put the units of newtons in there. And also don't forget putting in Young's modulus and inertia into your load per unit length is not typical, but we're doing that so that everything simplifies nicely. And it's not messy carrying everything through because now our differential equation is a nice clean fourth derivative of Y equals 20x. All right. So let's go ahead and just say over here to the left, complementary. Oh, dogs. We said earlier that it's fine if you just want to go ahead and state that the complementary solution is C1x plus C1 plus C2x plus C3x squared plus C4x cubed. This is completely fine. We have no issues with that. If you do get that wrong, however, and you've shown no work, then we cannot give you partial credit. So it's really important that you know this or you show your work, one or the other. Okay. All right, now for the particular part. We notice that we have an x term here, and then the derivative of 20x would be 20, so we'd think we need a constant as well. The problem is we already have an x term and we have a constant term. So we'd think we need to multiply by x and get x squared and x, but we have those as well. Multiplying by x again would give us x cubed and x squared. We already have those. Multiply by x again, giving us x to the fourth x cubed. Almost, but we already have the x cubed. So we've got to go one more, and that way we have x to the fifth, x to the fourth, and now we're free and clear. Okay, so it's very important that we get all the way out of any repetition or any linear dependence whatsoever. All right, and same thing, we need four derivatives of this. So yp prime will be 5ax to the fourth plus 4bx cubed. Yp double prime will be 20ax cubed plus 12bx squared. Yp triple prime is going to be 60ax squared plus 24bx. And then the fourth derivative of yp is going to be 120ax plus 24b. And that fourth derivative of y is supposed to be equal to 20x. So 120ax plus 24b should be 20x. Your coefficient of x on the left is 120a, so that should be 20. And the constant on the left is 24b, but there are no constants on the right, so that should be 0, which means b is 0. It's always nice when something zeroes out. A is going to be 20 over 120. Okay. And so 20 over 120 reduces to 1/6. So your YP is going to be 1/6 x to the fifth plus 0. So you've got your complementary part, and you saved a lot of time by just knowing this is always going to be the case for the complementary part of your beam deflection problem. And now you found your particular part, which you are going to have to worry about linear independence. Now we're going to put them all together. So we have y equals C1 plus C2x plus C3x squared plus C4x cubed plus 1/6 x to the fifth. Now, I don't think this one works out super nicely with the numbers. All right, let's remind ourselves of what our conditions are to help us, because we need to find C1, C2, C3, and C4. Let's go back up. So I can start with this guy, y of 0 equals 0. So y of 0 equals 0. So 0 equals C1 plus. Now every term will be 0 after that, which means C1 is 0. So I'm just going to come on up here and say 0. Let's go ahead and take the first derivative of y. Derivative of 0 is 0. Derivative of C2x is C2. Derivative of C3x squared is 2C3x. Derivative of C4x cubed is 3C4x squared. And then here I'll get 5/6 x to the fourth. Let's see if I can use a condition for y prime. Scooting back up to the top. And there it is. Y prime of 0 equals 0. Let's use that one. So y prime of 0 equals 0. So 0 equals C2 plus, and then all of these terms will be 0 after that, which means C2 is also 0. Very nice. So I'm going to go ahead and call that 0, and let's come on over here and call this term 0. All right, now come on back up here. Let's see. I need to find a second derivative and a third derivative to use my other conditions. So let's do that next. All right, so second derivative. Let's come on down here. Second derivative. Derivative of 0 is 0. Derivative of 2C3x is 2C3. Derivative of 3C4x squared is 6C4x plus. Now this will be 20 over 6, so 10/3 x cubed. And then one more time coming back up here, I want to use y double prime of 10 equals 0. So I have 0 equals, write this out, y double prime of 10 equals 0. So 0 equals 2C3 plus 6C4 times 10 plus 10/3 times 10 cubed. Now I can't divide both sides by 10, but I could divide both sides by 2 to clean this up a little bit, because everything here is even. And that'll cancel here. This will give me 3, and then this will give me 5. So now I have 0 equals C3 plus 3 times 10 is 30, C4 plus 5 times 10 cubed is 1,000, so 5,000 over 3. So that's still an equation in 2 unknowns, which I don't love. Let's see if I have another condition to help me. Yep, I need a third derivative. So third derivative, y triple prime. Let's see, derivative of 2C3, that's a constant, that'll be 0. Derivative of 6C4x is 6C4 plus, if I bring this 3 down, that's going to give me 10x squared. And we had that y triple prime of 10 was 0. So 0 equals 6c4 plus 10 times 10 squared. So I can't really, I mean, I could divide both sides by 2 here, but there's really no reason to. I've got 10 cubed here, so 1,000. So 6c4 equals negative 1,000. So C4 is negative 1,000 over 6. These are both divisible by 2. C4 is negative 500 over 3. On the exam, by the way, we won't give you anything with fractions that's ugly. Don't worry, that's not going to happen. We can put that back in up over here. 0 equals C3 minus 30 over 3 is 10 times 500 is 5,000 plus 5,000 over 3. So you've got negative 3 over 3 plus 1 over 3, so that's negative 2 over 3 of them. So 0 equals C3 minus 2 times 5 is 10,000 over 3. So, you know what, I don't want to waste another piece of paper. Let's just squeeze it right here. C3 equals 10,000 over 3. So then I'm just going to go ahead and come back to my general solution. I'm going to rewrite this over here. C3, 10,000 over 3, x squared, plus C4, which is negative 500 over 3, x cubed, plus 1/6 x to the 5th. And that is my equation of deflection. So now I've given you 2 examples. One is of a simply supported situation where both sides of both boundaries are simply supported, and then one where you have an embedded side and a free side. And so you've got a little bit of everything. And hopefully that's enough to get through all of your practice problems. And then the homework. The solutions to number 2 and 3 are not done yet in the solutions manual, but they're right here in the video. So I might not get to typing them up, but you've got them here in front of you for the video. So you should be able to reference this, no problem. If I do get to typing them up, that would be great, but I am on limited time. So, just keep referring back to the video. And, obviously come to office hours tomorrow if you can.